Hello students, welcome to the Electrical Engineering YouTube channel. In this lecture, I am going to discuss the parallel operation of transformers. So two transformers can be connected in parallel to enhance the power rating of an individual transformer. So if we have the power transmission or power dissipation in the load as 100 megawatt, but we have one transformer whose rating is given as 50 megawatts. So we must have to connect a 50 megawatt transformer in parallel with the first one to enhance the overall rating, power rating of the combination 200 megawatts, which is actually the power rating of the load. So the two transformers can be connected in parallel by connecting the subsequent terminals with each other. So this in this diagram, this is first transformer A, this is the second transformer B, this is the primary winding, and this is the primary winding of the second transformer. Similarly, these are the two secondary windings. Now the upper terminal of the primary winding of the first transformer will be connected to the upper terminal of the primary winding of the second transformer, and vice versa. So we have defined two bus bars. This is the primary bus bar, this is the load bus bar. So practically two transformers can be connected in parallel by connecting the upper terminals with one bus bar and the lower terminals with the second terminal of the bus bar. So this is the load bus bar or the secondary bus bar. Same procedure will be applied over here. So there are several conditions which have to be taken into account to allow smooth and consistent operation of the parallel combination of transformers. The first condition is that the polarity should be same. Polarity means in this case the dot convention. So if we have a dot at the upper side of the primary winding and it is connected to the upper side of the second primary winding, so the dot will be at the upper side of both the primary windings. Similarly here, if the dot is at the upper side of the secondary winding of this transformer, then the dot should be at the upper side of the secondary winding of this transformer, and vice versa. So the polarity should be same. Voltage ratings or the turn ratio should be identical. The third condition is that percentage impedance should be equal in magnitude, and X over R should be same to avoid circulating current and operation at different power factor. So if this X over R ratio of the two transformers is not consistent, then there will be circulating current which will be flowing between the two transformers, and the operation of the two transformers will be at the different power factors. So now, based on these conditions, there will be three cases, and in the first case, this is the ideal case, and in this case, the voltage transfer ratio of the two transformers is same, and the X over R ratio of both the transformers is also same. So in this first case, which is also called the ideal case, this is the primary winding. These are the two secondary windings of the transformers which are connected in parallel. So this is the equivalent circuit of the transformer referred to the secondary side. This is the overall impedance of transformer A. This is the overall impedance of transformer B. IA is the transformer current flowing through the transformer A. Similarly, IB is the current flowing through the transformer B. And the addition or the sum of these two currents will be equal to I, and I is the load current which is flowing through this load impedance. So we can draw the phasor diagram based on the fact that the voltage transformation ratio and the X over R ratio both are the same. So this is our reference which is the secondary voltage V2, and this V2 is the voltage which is available across the terminal of this load. Now this is IA. IA will definitely be lagging behind the voltage V2. So this is the transformer current IA. This is the current IB flowing through the transformer B. And the important thing which has to be remember here is that the phases of these two currents will be same. Their magnitudes can be different, but the phases of these two currents will be same because X over R ratio to these two transformers is same, so both are operating at the same power factor. When the power factor is same, the phase difference between the voltage and currents of both the transformers will be identical. Now the magnitudes of these two currents can be different because the impedance of this transformer can be smaller than the impedance of the second transformer. So from this figure we can say that the impedance of transformer A is slightly higher than the impedance of transformer B. Due to this reason, the current of transformer A is slightly smaller than the magnitude of the current of transformer B. So the magnitudes are different because the impedances are different, but the phases of these currents will be same. And the vector sum of these two currents is I, which is the load current, and the load current will also be in the same phase. So we can write, based on this discussion, that I is equal to IA plus IB, and we can write V is equal to V2 is equal to E minus IAZA. So this is E2 can also be written as E, and E minus IAZA is equal to V2. Similarly, V2 can be written as this E minus IBZB. So when we compare these two equations, we can write IAZA equal to IBZB, and IA over IB is equal to ZB over ZA. So from current divider rule, IA is equal to ZB divided by ZA plus ZB into I. Similarly, IB is equal to ZA divided by ZA plus ZB into I, and V2 can be written as E minus IAZA. So it will be equal to E minus, this is ZA, and IA is equal to ZB over this term. So ZB over this term is equal to IA. So this is actually the parallel combination of ZA and ZB, and it is equal to ZAB, and this is the current I. So V2 is equal to E minus ZAB into I, E minus ZAB into I. So this is the overall expression which we can obtain from the case 1, and this expression will give us the voltage across the load. So we can extend our discussion to the explanation of this phasor diagram. Now this is IA and this is IB. IA is smaller than IB. It means that ZA is greater than ZB. So the impedance of this transformer is greater than the impedance of the transformer B, and similarly RA will be greater than RB, and XA will be greater than XB. Now since IA is smaller but RA is greater, but their product will be equal to IARA. Similarly, IB is greater and RB is smaller, so their product will be equal to IBRB, and their product will be equal. So IARA will be equal to IBRB, because one quantity is smaller, the other quantity is greater. So for both the transformers, the product of I and R will be equal to same. So this is IARA and this is also equal to IBRB. Similarly, this vector corresponds to JIAXA, and this will also correspond to JIBXB, because IA is smaller and XA will be larger, and IB is greater and XB will be smaller. But the product of IA, XA and IBXB will be similar. So this vector corresponds to IAXA, and this will also correspond to IBXB. So this is also written over here, and the vector sum of these two terms, IARA and IBRB, and IAXA and IBXB, will be equal to AC. So AC is a vector sum of AB and BC, and it is equal to IAZA, and this is also equal to IBZB, because from this comparison we have concluded that IAZA is equal to IBZB. So IARA will be equal to IBRB, and IAXA will be equal to IBXB, since the phases of these two currents are the same. So this is the discussion of the case 1, which is the ideal case. Now we will discuss the second case, in which the voltage transformation ratio of the two transformers is same, but the X over R ratio is different. So these two transformers have different X over R ratio but same voltage transformation ratio. Since the voltage turn ratio or voltage transformation ratio is same, so again the secondary voltages across the two transformers will be same. So this will be equal to E2, and this is also equal to E2, and this is actually V2. Now the difference will be observed in the voltage drop across these two transformers. So now we will have different phasor diagram. So this is the reference which is our secondary voltage V2. So this is IA and this is IB. Since the X over R ratio is different, so IB will be lagging behind V2 at some different angle, and IA will be lagging behind the secondary voltage by some different angle. So the phases between IA and IB will be different, and their vector sum will be equal to I, and I is equal to IA plus IB. So it will be lying somewhere in between them, and its magnitude will also be greater than the magnitude of these two vectors. So this is IB, and in parallel with IB there will be IBRB. So this is IBRB which is in parallel with IB. Similarly, this is IA. So IARA will be in parallel with this vector IA. So this is IARA, and their magnitudes will also be slightly different, and their phases will also be different. Now at the angle of 90 degrees there will be IBXB. So this is IBXB, and this is IBRB, and at an angle of 90 degrees this will be IAXA. So this is IARA, this is IAXA, and this is IBRB, and this is IBXB. Now the vector sum of these two vectors is equal to IAZA. So this is IARA, this is IAXA, and their vector sum is IAZA. Similarly, this is IBRB, this is IBXB, and their vector sum is IBZB. So again, according to this condition, since the voltage transformation ratio is same, so the secondary voltages or secondary induced EMF will be same, and it will be equal to E for both the transformers. So this same equation will be applied over here, and according to this equation, IAZA is equal to IBZB. Since the voltage transformation ratio is same, so V2 is definitely same, and E will also be same. Since the transformation ratio is same, so these two quantities have to be same as well. So IAZA is equal to IBZB. So the vector sum of these two vectors and these two vectors will be equal to IAZA, and it will also be equal to IBZB. So their vector sum is same, but these individual voltage drops across the transformer A and the transformer B will be different. And this is equal to E, which is equal to EA, and this is also equal to EB. So this is the second case, and in this case E is equal to this term and E is also equal to this term. From the comparison we can say IAZA equal to IBZB, and this is equal to A times ZAB, and ZAB is equal to ZAZB over ZA plus ZB. So this IZAB is calculated following the same calculations which we did for the case 1. So this is E is equal to V2 plus I times ZA. So the same expression is obtained over here. This is ZAB, and IA is equal to, so from here IA can be written as I times ZAB divided by ZA, and IA is equal to this quantity according to current divider rule, and IB is equal to this term according to current divider rule. We can multiply both the equations with V2, so this will become V2IA is equal to V2 times IB. Similarly, this is V2IB, and it will become V2 times I. Now this can be written as kVA of transformer A, and it is equal to this term multiplied by kVA of the load. Similarly, SB is equal to ZA divided by ZA plus ZB times S, and S is the kVA of the load. So these are the equations which we have obtained as a result of parallel operation when we have two transformers with same voltage transformation ratio but different X over R ratios. Now we will discuss the third case in which voltage transformation ratios are different as well as the X over R ratios are also different. So in this case we will have different secondary induced EMFs for the two transformers. So this is A, this is EB. So they will be different, and these are the transformer impedances, and their X over R ratios will also be different, and this is the load impedance ZL, and this is the current. So in this case we will obtain such a phasor representation of all the quantities. This is our reference secondary voltage V2, this is IB, this is IA. Since the X over R ratios are different, So IB and IA will be lying at different phases, and this is their vector sum, which is I. Now in parallel with IB we will have IBRB, and in parallel with IA we will have IARA. Since RA is a real number, so IA and IARA will have the same phase, and this is true as well for IBRB. So this is IBRB. Now at an angle of 90 degrees we will have IBXB, and this is actually IBRB, and this is IBXB, and their vector sum is IBZB. So this is their vector sum. Similarly, this is IARA, this is IAXA, and their vector sum is IAZA. So this is IAZA, which I have mentioned over here. Now the vector sum of EA, vector sum of V2 and IBZB is actually EB. Okay, so this is V2 and this is IBZB. So their vector sum is this EB, and this is V2 and this is IAZA, and their vector sum is actually equal to EA. So EA will be starting from here and it will be terminating at this point. So in this case, all the quantities will have different phases. So all currents, all voltage drops, and all induced EMFs will be different in this case. So the calculations associated with all these quantities in the third case will be slightly difficult. So we will have to take care while deriving the expressions for the circulating current, the individual currents of the transformers, and the induced EMF at the two transformers and the secondary voltage at the load. So EA can be written as IAZA plus I times ZL. So we will have different KVL expression for the transformer A. So EA will be equal to IAZA plus I times ZL. Similarly, EB is equal to IBZB plus I times ZL. So this is written over here, and I is equal to IA plus IB, and it will also become IA plus IB. So EA minus EB, if we subtract this equation from this equation, IZL will be cancelled out, and we will have IAZA minus IBZB, and IA can be written as EA minus EB. So we can rearrange this equation and it will become EA minus EB plus IBZB divided by ZA. So we will substitute this equation into this equation. So IA will be substituted in this equation and we will get EB. So EB will be equal to IBZB plus we will write this expression in place of IA, and this is IB times ZL, and this will become ZB plus ZB divided by ZA into ZL plus ZL times IB. So we will collect all the terms which involve IB, because we will take IB as common at the end. So this term has IB, so this is ZB, and this term has IB, so it will become ZB over ZA times ZL. So it will be placed over here, and this term is ZL times IB, so we will write ZL over here and we will take IB as common. All other terms, EA minus EB divided by ZA times ZL, will be written separately over here. Now we will multiply this whole expression with ZA, so it will become EB ZA equal to ZA ZB plus ZB ZL plus ZA ZL times IB plus EA minus EB times ZL. So IB will be equal to EB ZA minus this term. So this term is EA minus EB times ZL. So we can place this term over here and it will be written as minus EA minus EB times ZL, and this term will be divided, so it will become ZA ZB plus ZA plus ZB times ZL. So this is IB, and from the symmetry we can write the same expression, similar expression for IA, and IA will be equal to this EA ZB minus it will become EB and it will become EA. So minus EB minus EA times ZL divided by ZB ZA. So ZB ZA equal to ZA ZB, and it will be written as ZB plus ZA. So it can be written as ZA plus ZB times ZL. Now this term is minus EB minus EA for IA, and we can multiply this minus inside, and it will become again EA minus EB. So minus EB minus EA can be written as plus EA minus EB. So this is the expression for IA. Now we can write I, which is equal to IA plus IB. So when we add these two currents, this term and this term will be cancelled out, and we will get EAZB plus EBZA divided by this expression. Now we will divide the numerator and the denominator by ZAZB. So this numerator will become EA over ZA plus EB over ZB divided by 1 plus 1 over ZB plus 1 over ZA times ZL. So it will become 1 plus ZL divided by ZB plus ZL divided by ZA. And from here we can take ZL as common, and it will become this term divided by ZL, and it will become 1 over ZL, it will become 1 over ZA, and it will become 1 over ZB. So this is the expression which we will have for the current I. I is the load current. So the secondary voltage V2 can be calculated by V is equal to I times ZL. So this is I. So when we multiply it with ZL, this will be cancelled out, and we will get this expression for the secondary voltage. So in this case, the X over R ratios are not same for both the transformers. So there will be circulating current, which we have to calculate somehow. So in order to calculate the circulating current, we have to run this combination of transformers at open circuit condition. So if we make it open circuit, or if we equate ZL equal to infinity, then this current I will be equal to 0, and there will be only circulating current which will be starting from this transformer A, and after this point it will be absorbed by this transformer B, and it will continue to circulate between the two transformers since there is a zero current at the load, and the load is removed to make it open circuit. So in this case, the load current will be equal to 0, I will be equal to 0, and ZL will be equal to infinity, and we can calculate the circulating current IC by assuming ZL equal to infinity in this expression. So when we put ZL equal to infinity in this I load expression, it will become 0, and if we put this ZL equal to infinity in IA and IB expressions, then we will have to calculate these two currents by using the limits. So I have written IA over here again. So this is IA, and this is the expression for IA, and we will have to equate ZL equal to infinity. So we will have to divide both the numerator and the denominator by ZL. So it will become EAZB divided by ZL plus EA minus EB divided by ZAZB divided by ZL plus ZA plus ZB. So in this expression, if I put ZL equal to infinity, these two terms will be equal to 0, and we will have EA minus EB divided by ZA plus ZB. So this current is equal to the circulating current, which is IC. So similar procedure can be adopted for IB, and if we do the same operation for IB, we will get minus IC, because for IB there will be a negative sign over here, and it will be equal to minus EA minus EB divided by ZA plus ZB, and it is equal to minus AC. So from this figure, it is clear that if circulating current is flowing in this direction for transformer I, for transformer A, then for transformer B it will be flowing in the opposite direction. So if the circulating current is IC for the transformer, it will be minus IC for the transformer B. So I think it is very much understandable to you, and it was all very healthy and important discussion for parallel operation of transformers. We have discussed all the three cases. If we have same voltage transfer ratio and same X over R ratio, the first case, And if we have same voltage transformation ratio but different X over R ratios in the second case, and in the third case we have the different voltage transformation ratios and the different X over R ratios, the final expressions of the currents and the voltages will be different. So I hope you have enjoyed and understood today's lecture. For watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.